Yeah, I know. That doesn't seem like it's levitating. But it is. Let me explain.
This fidget toy is very interesting. Not because it's spinning. I mean, it's a fidget toy, that's a given. It's interesting because this part is not touching this part.
This video was brought to you by OnSap.
These two parts are a very precise fit. Their diameter is very close to each other, but not exactly the same. This allows for a very small gap that traps air between the two walls. When you spin it, the rotation creates a dynamic air pressure all around that separates the solid surfaces and effectively creates a floating spinning top.
On its own, this toy is pretty cool, but it became much cooler after I saw this video.
This video features a rim-driven thruster, which is basically a fan without a center shaft. It doesn't have a center shaft because it doesn't need one. Normally, a fan needs to be connected to a motor, but in this case, the fan itself is the motor. This matters because in a fan, any fan, most of the noise and inefficiencies come from the tips of the blades creating vortices that collapse into turbulence. On a rim-driven fan, the blades are inverted, and because of the way circles work, the tip speed here is very low.
Now, what does that has to do with this? Well, imagine this. A rim-driven jet engine that uses the combustion gases to make the fan float and at the same time to make it spin. We got the floating part pinned down, so how do we make it spin? Well, with tiny rockets, of course.
So, this right here is a prototype that I built that uses compressed air, and the tiny rocket nozzles are right here. The air comes through here, creates a pocket of pressure that makes the fan float, and gets exhausted through the tiny nozzles. Because these are tiny nozzles, we can think of them as tiny rockets that push this way, thus making the fan rotate. This was not easy to build, because like I said before, these two diameters need to be almost identical. If they're not, the air leaks through here instead of coming out of the tiny nozzles, and that is no bueno. The fidget toy I showed you earlier is made by a company called Matmo. They make a bunch of different toys like this, and after some cheeky research, I realized they use high-precision CNC machines to get the insanely high tolerances needed to get the air cushion effect. I don't have high-precision CNC machines, so what I did was, I 3D printed the fan using a resin called precision resin on my Form 4 resin printer, then I machined the cavity very slowly on a block of acrylic, until I got a very tight fit. Too tight, some might say. To make it less tight, I brushed both parts with headlight polishing fluid and manually rotated the fan until the friction became very, very small. It was a tedious process, but it did work pretty well. Unfortunately, this is not good enough because this uses compressed air, but my end goal here is to make a jet engine that uses combustion gases. But I can't do that because this is resin and this is acrylic, and both would instantly become the fuel for the combustion.
I basically need this, but in metal. I do have a CNC machine, but I don't think I'm gonna get the precision that I need with it. So, using the wise words of my grandfather, if you can't make it, just buy it. He used to say this when I handmade him birthday gifts. It's fine. It was a long time ago. I'm fine.
In this case, by buying it, I mean paying someone else to make it for me. This is an online service called JLC CNC that makes metal precision parts. They can get precisions of 0.05 millimeters, which is roughly the thickness of a human hair. I uploaded my 3D models to their website and ordered the fan to be made out of aluminium, so it's light, and the rest of the parts to be made out of brass, so it's slippery, just like in the fidget toy.
The part should take about a week to get made and get here, and that should give me just enough time to build a very important part of this project, the combustor. So, I'm treating this project as a rocket engine that has a fan as its nozzle. Now, with that being said, the nozzle is already being made, but I still need something that burns stuff, a combustor. I was thinking about how I should go around building that, and then I started playing with this.
This is a tiny camping stove I have, and it caught my attention because it's really good at burning gas. The flame is really uniform and it comes out without almost any turbulence. It's mesmerizing how laminar it is. In my head, I thought, yeah, this burns well at atmospheric pressure, but it wouldn't work as a rocket. Following that thought, I 3D printed an adapter so I could connect compressed air to the inlet and increase the pressure. And to my surprise, it still works. So I went a step further and placed a glass tube on the burner and made an impromptu nozzle out of graphite. And that's where things got interesting, because this tiny camping stove became a full functioning rocket engine, and that made me really angry.
I understand this might not be news to you because, of course, that a thing that is made to burn stuff. But let me tell you something. This is normally not this easy.
You see, I've been trying to make a combustor for rockets and jet engines for a while, and they normally work, but not like this. They either are too turbulent, only burn on a certain part of the combustion chamber, or the thing that confuses me the most, they work perfectly without a combustion chamber, but then I attach one and for some reason they either don't work or become a nightmare to ignite. All of this to say that I decided to get to the bottom of this and truly understand why this works so well. With that knowledge, I can finally design a proper combustor. So I took a closer look. The gas is injected by a 0.4mm nozzle and pulls in air from the sides using 4 holes that are 7.5mm in diameter. From there, the gases travel through a 10mm tube and hit this wire mesh that I'm guessing is to force the gases to mix. It's not easy to spot, but the mesh is right there. On the top of the burner, the mixed gases come out of these 1.4mm holes. There's 130 holes divided radially across 4 rows that I manually counted in the name of science. I wanted to know if the mesh really did help mix the gases, so I removed the top part of the burner and tried it without the mesh, and for the same amount of gas, without the mesh, the flame blows out. This was still not conclusive though, because the top part has this expansion cone, and maybe it's this geometry that helps and not the mesh. To make sure, I cut a bit of steel wool to act as my mesh and put it inside of the tube, and as you can see, there's improvement. I think I have another theory. So, the area of the 130 holes right here is 3 times bigger than the area of the tube right here. I'm guessing the reason for that and the expansion cone is to force both gases to slow down. You see, there's this thing called flame speed. It's the speed at which a flame propagates through a mixture of air and fuel. In this specific case, we are burning air and propane that at atmospheric pressure have a flame speed of 40 centimeters per second. This means that if the gases are traveling at a speed greater than the flame speed, the flame can't keep up and it's blown out. Initially, at the nozzle, I know the propane is going much faster than 40 centimeters per second, because this can has 4 bar and that is more than enough to make it accelerate to the speed of sound. But, and this is just conjecture on my part, after the gases travel through the tube and the cone that have an increasing area, I'm guessing the gases slow down a lot. To make sure, I connected the burner to my anemometer, which is a device that measures flow speed, but the anemometer didn't really detect anything, which makes me believe that either my anemometer is broken, or in fact the gases are really slow by the time they get to the outside world. I really wanted to know for sure, so I used this online platform called SimScale to run a flow simulation, and lo and behold, those gases are going slower than a snail on slow motion. It feels good to know.
Sponsor time.
Every single 3D model in this project was designed using Onshape. Actually, not only this project, but all my projects from the last 2 years. Onshape is a cloud-based application that you can use to design, share, animate, and test your 3D models. Because it's a cloud-based application, you don't need to install anything, you don't need to save anything, you don't even need a computer to use it. Onshape is the foundation to all my projects. I really like it, but don't take my word for it. Even companies like Boom that are designing supersonic airliners that fly at 1.7 times the speed of sound prefer Onshape. Onshape, it's an amazing tool for engineers. Any kind of engineer. So if you're an engineer, definitely check out Onshape. You can get up to 6 months of the pro version for free using the link in the description. I am aware that all that I just said might seem a little bit biased because, well, they're sponsoring me, but they are great. I mean, being sponsored is like a lucky side effect. So give it a try. It's great. You're gonna love it.
Now, that was very educational, but I can't just use this burner because it's too big. I designed the fan casing to have a 1/2 inch thread on the bottom, simply because I had this brass tube with the same thread laying around, and I thought, combustion chamber? I have a simple brain. The mission now is to build a rocket around this water connector. To do that, I use this free software called RPA. I reiterate, free software. To calculate the amount of air in propane, you put the pressure you want for the combustion chamber here. I'm going with a modest value of 2 bar. The nozzle diameter we also know because the fan has 36 tiny nozzles with 1 millimeter in diameter, which is equivalent to an area of a 6 millimeter hole. I chose my gases, atmospheric pressure here, and shaboinks. Here are the mass flows we need. For the injector, I'm going to use this T connection and plug the air through here and the propane through here. But because the recipe for combustion requires much more air than propane, I need to use a smaller hole for the propane. And to get the size of the hole, I took some equations from the NASA website and plugged them into an Excel sheet. That Excel sheet spat out a hole of 0.6 millimeters in diameter, which by pure coincidence happens to be the exact same size of the brass nozzles I use on my 3D printers. Now, While I was confirming the Excel results using SimScale, I noticed something. This is a simulation using a single 2mm hole, and this is a simulation using 16.5mm holes. They both have the same total area, they both have the same pressure and mass flow, but they are not the same. The gases with the 16 holes slow down much faster, which means more tiny holes is better than a few bigger holes. Feel free to quote me on that. Okay. I want to make this as simple as possible, so this is the aforementioned 1/2 inch brass tube, and this is an 1/2 inch plug that I'm going to transform into an injector. First, I make many tiny holes using a very tiny 0.5mm drill. I'm going to be honest with you, I broke a few of these. They are really tiny and fragile. Then I silver solder it to another 1/2 inch plug. Silver soldering is like welding for people that can't weld, so perfect for me. Then I screw in a 1/8 of an inch connector so I can attach this to the T-joint I mentioned earlier. As a temporary nozzle, I can use this adapter, which has an internal diameter of 6mm, which is basically the same as the fan. The only thing missing is ignition, and the ideal is to ignite the gases where they are low speed and well mixed. So I bought this tiny spark plug, and I placed it right here, in the middle.
Rock and roll!
A rocket and roll!
Nice!
I guess all that mathy simulation was worth it. Okay, first of all, just from the noise alone, I can tell this is without a shadow of a doubt the best rocket I've ever built. Now, a funny thing happened. As I tuned the amount of air in propane, the rocket would reach this equilibrium state in which the sound was very smooth and the exhaust just disappeared. This is kind of sad because I couldn't get Mac diamonds on camera, but what you normally see on a flame is the unburnt particles glowing, which means this rocket is achieving full combustion to the point that it's burning solid carbon. There was a point in which the nozzle turned so red that it seemed photoshopped. It doesn't even look real. I also learned a neat trick. If I shut off the main valves when the rocket is at max performance, I can just start it immediately afterward. As for the thrust, RPA says it should be putting out 2.7 kilograms of force, which is not bad for such a tiny rocket. The best I could do to confirm this was to put a sheet steel metal in front of it, and as you can see, the entire tripod freaking moved. I also put a tomato in front of it because, of course I did.
What? I want you to burn. Don't fall. Wait, hey! Look what just arrived. Great timing, right? Is what I would say if I was a liar. In truth, the parts arrived 3 days ago, but I was out of the country doing important stuff. Anyway, they arrived in these tiny bags and they were covered in oil. I'm guessing it's to protect them from the oxidation. They look pretty cool and shiny, but that is not what is important to me. What's important to me is the dimensions, and for those, I don't even need a caliper.
Just look at this gorgeous fit. Look at that. Doesn't have a lot of give, can barely move it. I think I'm gonna test it with compressed air first, just to make sure everything moves, and then rocket. The fan did work pretty well, but I had to remove the brass retainers I ordered because they were causing too much friction. Instead, I used this aluminum bracket that I machined that have these graphite rods from pencils. Graphite is like the holy grail of friction. It worked perfectly.
Alrighty then. It's time to give it a test with combustion. Let's see if my neat trick still works. The fan is stuck.
Why? Why is a stupid question, my young past self. The real question is how, and the how is attributed to the what, that in this case is thermal expansion. You see, metals expand when they get hot. In this specific case, the fan reaches about 350 degrees Celsius and expands almost 0.3 millimeters, which might sound like it's nothing, but it's enough to stuck it inside the brass housing. Talking about the housing, brass is also a metal, right? Shouldn't it expand as well and compensate for the fan expansion? The housing does expand, but brass expands less than aluminum, and this part is bigger and thicker, so it takes much more time to heat up.
Okay, I think this should be an easy fix because I know how much the fan expands, so if I remove the 0.3 millimeters from the outer diameter, when it does expand, it should reach optimum dimensions again, right? Okay, I think we're ready for round 2. As you can see, it's a little bit more give. Let's see if that works. What? Is it still getting stuck? I hate waiting for the compressor. No! I have to remove more? I guess so. Okay, I removed 1/10 of a millimeter all around the fan, so let's see if it works now. What? No! Oh no. My fan has a hole in it.
Yeah, that was pretty sad. Even sadder was me trying to learn how to solder aluminium to fix the fan. That didn't go well. Aluminium is not that easy to solder. I think I made it worse. Now, what I should have done was order a couple more fans. They would be here in a week. But I don't know if it was shame, desperation, or the fact that I wanted to prove my grandfather wrong. I decided to try and machine one. What followed was a month of me failing spectacularly at doing so.
No.
Come on. Yeah, my milling bit is not long enough. I need to get a bigger one.
You see, machining one side is actually not that hard. I got that down in the first week. The problem arises when I have to do the other side, because to turn it, I have to move it. And by doing so, I lose the alignment on a part that needs to be super precise and spinning at thousands of rotations per minute.
Okay, so the challenge that I'm facing right now is that, as you see, this side is machined, right? But I have to turn it to machine this side of the blades. The problem is, if I do it manually, I lose the alignment. But I have an idea. What if I use this center hole to directly screw in the fan into the build plate, and then I use the tool itself to push it into alignment? I mean, it can't be misaligned if it was the tool that put it there, right?
To machine the center cavity, I used the 4th axis that came with the CNC machine. It's like a kebab rotisserie, but for aluminium. Okay, the only thing missing is the little 1mm nozzle holes. My first plan was to 3D print some jigs and drill them manually, but that didn't really work out. I ended up breaking drill bits inside the holes and then crying for 2 hours because I had to start over. Now I have a new nozzleless fan, and this time I 3D printed a jig, but to make the holes in the CNC machine, because I think what messed the first plan was me having my shaky hands involved.
That was the last one. I'm finally done. Take that, Grandpa. I cannot put into words how proud of myself I am for being able to machine this part. And it's for that reason that I refuse to let it melt. There's a lot of time and effort involved in this little part. But luckily, I have acquired a very interesting piece of information. Aluminium rust is not metal. When aluminium rusts, it forms a layer of ceramic material called alumina that can withstand up to 1000 degrees Celsius. So the first order of business, of course, is to forcibly rust my fan using sulfuric acid and electricity. This process is called anodization. I think I'm saying it right. And it's done industrially all the time to make aluminium less prone to scratching. Also, if the part is already rusted, it becomes resistant to corrosion, which is a weird thing to do because it's like getting wet because you don't have an umbrella. Anodization is pretty cool. And I'm pretty silly because I can protect the fan all I want, but it's still gonna expand because of the heat and get stuck in the housing. What I need to do is get rid of the heat, or at least minimize it. What if I inject water into the combustion chamber?
If I inject water inside the combustion chamber, the water will absorb some of the heat and turn into steam. Not only would this cool the engine, but also get me some extra pressure. I bought this copper tube and I'm going to bend it in a coil and make some holes in it to inject the water. Except this is not copper, it's aluminium disguised as copper. I got scammed. It's like I'm being haunted by this goddamn soft metal. It should be fine. It's gonna be filled with water, and water is pretty good at protecting stuff from heat.
Steam rocket test number 1.
My hand here.
Okay, time for a cheeky test.
It worked! Yes! Finally!
Oh, I lost a month of my life because of you. Witness me! I am aluminium's worst enemy. Revenge is a dish best served hot and steamy. Nice. So, it was a difficult project. There was a lot of challenges, a lot of failing, but also a lot of lessons learned. And I would say the most important lesson that I learned was tomatoes are disgusting. Just kidding. I already knew that. See ya!